Hello students, so today we can start with a new topic, that is interfering anions. Interfering anions. Interfering anions. Okay, as the name suggests, no, they interfere. These are the anions which interfere in the cation analysis. As the what's interference is all about. It's actually coming in between, disturbing the cation analysis. So sometime we expect during the cation analysis, I told yesterday, you have to follow a scheme. First group, second group, third group, fourth group, fifth group, like that. While the analysis of a cation, when you show a precipitate, for example, when group 3 reagent is added, you show a precipitate, means you are expecting it's a group 3 cation. But due to this, these interfering anions, some unwanted precipitate may occur, or some our reagent may be utilized for utilized by these interfering anions, like that. Totally, during our cation analysis, these anions can interfere in the proper cation analysis process. So that what interfering anions is all about. It's not all the anions interfere. There are some anions we can list, they actually can interfere in the cation analysis. They are, let me list first one, arsenite. Arsenite, that you can represent AsO3 3 minus, arsenite. Second one, arsenate. Arsenate, AsO4 3 minus, AsO4 3 minus. Then chromate, that is CrO4 2 minus, chromate. Then the fourth one we can discuss, that is oxalate. C2O4 2 minus, oxalate. Then borate, BO3 3 minus, borate. Sixth one, after borate, is fluoride. F minus. Then one more, that is phosphate. PO4 3 minus. So these are the interfering anions, that you cannot, especially this becoming important, because during the cation analysis these anions can interfere in the proper analysis. So what are they? First one, arsenite. ASO3 3 minus, arsenate ASO4 3 minus, chromate CrO4 2 minus, then oxalate C2O4 2 minus, borate BO3 3 minus, fluoride F minus, phosphate PO4 3 minus. So these are the interfering anions. Okay. So now let's see their interference, what they actually do. So it is observed that arsenite, arsenate and chromate, these three actually interfere from the second group of cation analysis. They actually can interfere from second group onwards. So we can say they interferes in the second group of cation analysis, and here you will see they start interference from the third group. So they actually interfere from the third group of cation analysis, or they start the interference from the third group onwards. So this is the first point you can note, okay, where this oxalate, borate, fluoride, phosphate, they actually present, if that is present during the cation analysis, they actually not disturbing the first and second group, because these actually become soluble in acidic medium. In the previous class I told first and second group of cation analysis that we do in the acid medium, right? So these groups actually dissolving in acid medium, so they're not making any unwanted precipitation or something in the first and second group. That way they start interfering from the third group onwards. But these three influencing these three actually interfering from the second group onwards. Okay, that I will discuss. Especially they react with hydrogen sulfide. Okay, so and chromate actually utilizing the hydrogen sulfide and converting into sulfur. So they make their interference from the second group onwards. So that's the first point you cannot relate to the interfering anions. Now let's see what they actually do. There are three ways they can cause the interference. Okay, let's see how they interferes. Interference causes unwanted precipitation on addition of group reagent. So that the first point you cannot. How they interfere? First point, they causing unwanted precipitation. Unwanted precipitation. Unwanted precipitation. So what does it mean? So this is means that these groups actually causing an unwanted precipitate, which is we expect. For example, let me explain through an example. For example, arsenite, when it's in acidic medium, it's actually converted into arsenous acid. So H3AsO3. So arsenate, first we can discuss arsenite actually reacting with the hydrogen sulfide to form arsenic sulfide As2S3 plus 6H2O. So this is the way actually arsenite causing an interference. Okay. So what arsenite is doing? Arsenite, we know group 2 reagent. What is group 2 reagent? Group 2 reagent is dilute HCl plus hydrogen sulfide, right? So what if arsenite is there in the reaction mixture? What will do? Arsenite actually combine with the hydrogen sulfide to form arsenic sulfide, which is it appearing as a precipitate. So a precipitate will be form of arsenic sulfide. So that actually forms a precipitation group 2. So we can think think in two ways. When precipitate is forming, when diluted HCl and hydrogen sulfide is added, we think it's group 2 cations, right? That's what we expect. When a precipitate is forming on group 2, we expect it's a group 2 cation, but may not be. Maybe group 2 cations may be there, but if arsenite is present in there, arsenite will cause a precipitation of arsenic sulfide in presence of hydrogen sulfide. So actually caused an unwanted precipitation. Okay, arsenite actually interfered in the cation analysis, right? But normally we expect group 2 cation to precipitate, but no, it actually precipitate if arsenite is there, that is precipitated as arsenic sulfide. So that's a problem with the arsenite if that is present in the reaction mixture. So best thing we can do, there are two ways you can think. One thing you have to eliminate this interfering anions. So during the mixture analysis, there are normally 2 anions and 2 cations will be given. So the 2 anions first you identify. That's a normal scheme of analysis. First you identify anions. So after understanding these are the anions present in it, and these are the and out of which if these interfering anions that I told, the interfering anions, if that is present, it's very important that anion needed to be eliminated before you going into the cation analysis, because you can see they causing interference in the cation analysis. So that's a one method you can think. You have to eliminate the interfering anions before cation analysis. That's a one logical method you can think. Another method, no, we actually preparing sodium carbonate extract. Sodium carbonate extract for the anion analysis. No, that's a during the scheme, one student can understand. Sodium carbonate extract, we preparing the liquid part, the filtrate actually used for the anion analysis. Why we actually doing this? No, some of the anions may not be obtained from our normal mixture. So if sodium carbonate extract is prepared, the filtrate, the liquid part actually containing only anions. Okay, there is no interference of cations in that sodium carbonate filtrate. So actually that makes a very easy process, that the liquid part sodium carbonate extract filtrate only contain anions. So using that you can identify the presence of some of the anions, or no, it gives more clarity in terms of result. Okay, so in liquid part of sodium carbonate extract, that filtrate only contain anions, and the solid part, the residue during the filtration, the residue left in the filter paper or whatever that we obtain, we call the solid part as residue. The residue only contain cations. Now a student can think, during the sodium carbonate extract preparation, the residue only contain cations, filtrate only contain anions. So if you can able to separate it properly, no elimination process is not required, because what we actually mean it by elimination, we want to eliminate the anions, right, interfering anions. If you prepare sodium carbonate extract properly, the residue part only containing cations, the filtrate part only containing anions, means that made our process very much easier. Okay, so that's one of the way that nowadays most of the students are doing, using the residue. We actually doing the cation analysis. There the interference is not there, because anions are not present, while in the filtrate only anions are present. So sometimes cation can also interfere in the anion analysis. So using the filtrate of sodium carbonate extract, only anions will be there. So cations also would not interfere in the anion analysis. So that's a point also you can remember related to the interfering anions. So we discussed how arsenite is interfering. Okay, water plus arsenic sulfide, water plus sulfur is also forms, and sorry, I just made a mistake. Sorry. This arsenite actually treat with the hydrogen sulfide to form arsenic sulfide. So this forms a precipitate in the while group 2 cation analysis. So another point you can check how arsenate causing interference. So arsenate AsO4 3-, right? So in presence of acid it form arsenic acid. So H3AsO4, in presence of hydrogen sulfide it actually form H3AsO4, H3AsO3 first, that is arsenic acid, water plus sulfur. Okay, look at this, is actually arsenic, this is arsenate, right? This is arsenite, this is arsenate. Arsenate first actually converted into arsenite in presence of hydrogen sulfide, or you can say hydrogen sulfide here -2 oxidation state, here it's 0. So it's reducing the hydrogen sulfide to sulfur. So this is now what arsenate is doing. So arsenate is actually converting hydrogen sulfide to sulfur, and it's itself now converting arsenate to arsenite. Okay, it's a slight different. ASO3 3- is arsenite, ASO4 3- is arsenate. So this is what happening. ASO3 is forming. That reaction we already written, right? Once ASO3 is formed, that actually combining with the hydrogen sulfide to form arsenic sulfide and water. So after that second step which is again the first step. So the only difference is arsenate first converted into arsenite, then it again combined with the hydrogen sulfide to form arsenic sulfide. So that's the problem, it's interfere in the second group in such a manner, and unwanted precipitation of arsenic sulfide is forming. And look at this, what arsenate is doing. Arsenate is actually utilizing excess hydrogen sulfide. So hydrogen sulfide we supposed to pass for the precipitation of group 2 cations, but it actually can cause the unwanted precipitation of arsenic sulfide. So that what happened. Okay. Now what about chromate? Chromate, what is doing is actually it overutilizing, is utilizing the hydrogen sulfide. So you can see chromic acid first in presence of acid, HCl will be there in the medium. In presence of hydrogen sulfide, it actually forms chromium chloride. So CrCl3, chromium in the +3 oxidation state. So chromium chloride and water and sulfur. Okay. So water and sulfur will be formed. So what is the chromate is doing? Chromate actually converting the hydrogen sulfide to sulfur. At the same time, here chromium is in the what oxidation state? Here chromium in the +6 oxidation state, right? So chromium reduced to +6 to +3. So this is how it it causing its interference. It actually forming chromium 3 chloride, where it utilizing the hydrogen sulfide present in the medium will be converted into sulfur. So that's the problem with the chromate. So these will cause from group 2 cation analysis, because we know hydrogen sulfide is the one of the reagent of group 2. So definitely it causing interference. Now let's see another point. This is one of the way anion causing unwanted precipitation. Now let's see anion causing precipitation of metals outside their own group. So that's another way interfering anions can interfere. They causing an unwanted precipitation outside their group, which means we expecting, for example, calcium, strontium, barium, they are group 5 cations, right? So we expect calcium to precipitate at group 5, not in any other groups, right? But if oxalate or something is present, that can cause an unwanted precipitation in the group 3 itself. Let's see. Oxalate and C2O4, H2C2O4, that is oxalic acid for you. Oxalic acid, oxalate converted into oxalic acid in acid medium, and it react with ammonium hydroxide to form ammonium oxalate first, NH4 twice, C2O4. It's not chromium, it's C2O4. C2O4. Okay, C2O4 plus water, and the second step, this ammonium oxalate converting into, if calcium is present, calcium cation is present, they form calcium oxalate, CaC2O4, calcium oxalate plus ammonium chloride. So you can see actually calcium is precipitated in the group 3 itself, because in presence of ammonium hydroxide, this oxalate first converted into ammonium oxalate. In the second step, if calcium is there in the medium, okay, that actually precipitating in the group 3 itself as calcium oxalate. So that's a problem, because we expect calcium to precipitate in the group 5 cations, but if oxalate is present, calcium can be precipitated as calcium oxalate in the group 3 itself. So during the cation analysis, during the 5th group, if enough calcium may not be there, so calcium may not be precipitated in group 5, which we expect. So that's a problem with interfering anions like oxalate. Okay, so that's another way of interference. They actually causing precipitation outside their group. We expect calcium to precipitate in the group 5, but it's precipitated in group 3, again causing disturbance, right? Totally our scheme has been totally disturbed due to these interfering anions. So that's the two method we saw. First method, anion causing unwanted precipitation like arsenic sulfide. We saw in the second point they causing precipitation of metals outside their group. Now third way, anion causing the formation of stable complex ions in solution. That's the third way they can interfere. They can form stable complex ion. Stable complex ion. Now this is something now we study in coordination chemistry. Coordination compounds actually deals with the ligand and central metal ion forming coordinate bond, right? So that's the case with especially the anions like oxalate can form this coordinate bonds, coordinate compounds. So if oxalate is there, they can form some stable coordination compounds like MC2O4 thrice n minus 6. So this is a general method I represent metal. This M is a metal. Metal can be cobalt, chromium, manganese, iron, aluminium, etc. So these are the general cations, okay, which actually forming a stable coordination complex in presence of anions like this oxalate. So what they actually do, if anion is there in presence of a cation, they actually form these stable complexes like metal oxalate complexes. So they actually during the cation analysis if oxalate is there, that actually may not be available in their respective groups. For example, aluminium, if there oxalate is also there, aluminium oxalate complex will be formed. So there during the cation analysis in the group 3, aluminium may not be available enough because they actually formed a stable complex with this with this anions. So that's a problem with these interfering anions. So anions forming stable complexes in the solution. Okay, aqueous medium is required. So in the solution, so that why in the anion analysis may not be interfering much, but when they dissolves in acid, from the group 1 onwards we adding dilute HCl, so becoming a solution, right? So from there onwards it can form a stable complex ion, so which causing unwanted interference, like it forms a stable complex ions. So that's a way you can understand the interference. First point, they actually causing unwanted precipitation like arsenite and arsenate we saw. And the second case, they causing a precipitation outside their group like calcium precipitating in group 3, which we not expecting. And another point, they forming stable complex ion with the anions like oxalate. So this is the way they can interfere in the cation analysis. Now, as I said, it's very important you have to eliminate the anions, because they can cause the unwanted interference during the cation analysis. So it's very important we have to learn the elimination method. So how we can eliminate these interfering anions? Elimination of interfering anions. Elimination of interfering anions. So theoretical point of view, you have to learn this, because sometimes question can ask how interferent anions can be eliminated. But in practical purpose, you can use the technique that I told, using the sodium carbonate extract residue. You can directly go for cation analysis, because their in anions won't be there. So that technique you can use in the while the practical purpose. But theoretical purpose, you have to learn how this can be eliminated. So the first point, let us start with arsenite and arsenate. So now we saw they actually forming a precipitate in the second group, right? Arsenic sulfide. So nothing we can do when hydrogen sulfide is passed, arsenic sulfide will be formed. So arsenic sulfide will be precipitated in group 2, and we have to make sure once a precipitate is formed, you have to centrifuge it using the residue. You have to separate it and filtrate the liquid part. Again you pass hydrogen sulfide, again precipitation will be occur. You have to separate using centrifugation. Again the liquid part you have to pass hydrogen sulfide. like repeatedly you have to pass hydrogen sulfide, so that you have to make sure are the arsenate or no group 2 cation present is precipitated. Okay, that what you have to make sure. Okay, that what means no, definitely arsenite is there. Okay, group 2 cation if present, that also get precipitated. And once no group 2 is everything is done, now then you can, using that residue, using that solid part, you can go for the analysis of cation, no group 2 cations. Now each cation has specific test, using that you can identify the respective cations. So how can you eliminate arsenite and arsenite and arsenate? No way. You just pass hydrogen sulfide. You actually have to make sure you're precipitating the group 2 itself. You just repeatedly pass hydrogen sulfide, it will precipitate as arsenic sulfide. Again you pass hydrogen sulfide to the filtrate, make sure all the arsenite and arsenate are precipitated in the group 2 itself. And during the cation analysis, you may get arsenic as one of the cation, that you have to understand. It may be due to the this interfering anions. Okay, but if some other cation is there, that also you can that also will be answered if no group 2 cation is present. Okay, so that's a method you can utilize for the elimination purpose as well. You pass hydrogen sulfide, you can see arsenic sulfide will be formed, that you repeatedly pass, you can make sure all the arsenate will be eliminated. So that method, reaction already I written, because same reaction. Okay. Okay, now let us now think about the arsenate is slightly different in presence of ammonium iodide. It's actually converted into arsenite. So H3SO4 in presence of an acid and this ammonium iodide, that iodide actually helping the conversion of ASO4 into ASO3. So that you can specifically note H3ASO4 in presence of H plus and I minus. So you can use ammonium iodide as a reagent, which helps for the conversion of ASO4 into ASO3. So we actually want a conversion from ASO4 to ASO3. Then only we can precipitate as arsenic sulfide, right? So H3SO3 will be there, and iodide will convert into iodine, and water will be obtained. So if needed, you can use ammonium iodide for the conversion of arsenate to arsenite. So that's the point you can remember. You have to convert arsenate into arsenite, then only you can convert it into arsenic sulfide. So that's one step you have to remember about elimination of arsenate. Okay. Now let us think about chromate. How can you eliminate chromate? Chromate you can eliminate using concentrated HCl. You take a china dish, you just take the mixture, you add concentrated HCl just enough to cover it, then just boil it, so that all the chromate will be evaporated off. So the chemistry is CrO4 2 minus will convert to corresponding chromium chloride, chromium 3 chloride, CrCl3, and chloride ion also forming Cl minus, water, and finally chlorine. So actually our point is chromium plus 6 is reduced to chromium 3 plus 3 and Cl minus. So this is you can understand this is one of the disproportionate reaction, right? It plus 6 to plus 3 plus 6 to minus 1. So chromate is eliminating as either chromium 3 chloride or chloride ion or even chlorine gas itself. It's eliminating. This chromate part is eliminating in presence of concentrated HCl. So that's the way you eliminating chromate using the residue. You can dissolve in water and you can centrifuge it. Using the centrifugate, you can you go for the cation analysis. So that's the way you can eliminate chromate using a using concentrate HCl. That better before cation analysis. Once the mixture is there in your hand, you first treat with the concentrate HCl by taking in a china dish and boil it and just eliminate the liquid part. You evaporate it nearly to dryness to make sure all the chromate is eliminated. So next we can think about oxalate. Oxalate is very important, very important, that's needed to be eliminated. So the best way you can eliminate chromate oxalate, it's by heating. You take a china dish, you take the mixture, you heat for continuously for nearly 20 minutes. If you heat it strongly, all the oxalate will convert into either carbon dioxide or carbon monoxide. So that's the way you can eliminate oxalate. Let me write the reaction CaC2O4. Oxalate when you heat it strongly, it converted into calcium carbonate and carbon monoxide will be eliminated. Or another way you can think, if you heat strong enough, calcium oxalate can convert into even calcium carbonate can decompose and calcium oxide will be formed and carbon monoxide and carbon dioxide will be eliminated. So that's the way you can imagine. It's all about we want to convert this oxalate into some other compound so that these do not cause unwanted interference. So calcium oxalate converting into mainly carbon monoxide and carbon dioxide gases, right? So they actually gases will be eliminated. So that's the way you can eliminate oxalate as well. Borate and fluoride, these are now the technique we're using in presence of concentrated HCl. We just take a mixture, take a china dish, you add concentrated HCl so that borate will convert into boric acid and HF fluoride will convert into fluoric acid. So HF and H3BO3 respectively will be formed. So that is volatilizable gases. So that will evaporate off if you heat it. If you heat this, if you boiled it, they will be eliminated. So by boiling this borate and fluoride in presence of concentrated HCl, they escaping as corresponding volatilizable gases. So that's the way you can avoid or eliminate the borate and fluoride respectively. For example, if you write the reaction BO33 minus in presence of HCl converting into H3BO3 boric acid, which is an eliminating, which is an easily escapable gas. Okay. H3BO3 and 6Cl minus will be formed. So this is the way you can now eliminate H3BO3. How much mole? It's 2 moles. Okay. So this is the way you can eliminate the borate. Similarly, fluoride. Again, the method is same. You add a concentrated HCl in a china dish, and now this will be, the fluoride will convert into HF. So HF will be formed, and this, remember, this both cases, this HF and H3BO3 both are easily escapable gases, so they will eliminate easily. Similarly, this phosphate also you can eliminate as either as zirconium phosphate. That's one of the best method we can see. In presence of zirconyl nitrate, this phosphate can convert into corresponding zirconium phosphate. For example, ZrO NO3 twice. In presence of phosphate and HCl, So look at this is zirconium nitrate, zirconyl nitrate, okay. Zirconyl nitrate in presence of phosphate convert into zirconyl phosphate. So that will be precipitated, that precipitate you can remove, okay. So before, no, and especially after the group 2 cations, you eliminate hydrogen sulfide, then now the zirconyl nitrate will be added. Sorry. Okay, let us wind up now. Just there's the two way you can eliminate by treating with the ferric chloride and by treating with the zirconium nitrate or zirconium chloride. Using these two reagents, you can eliminate phosphate. Okay. Thanks for listening. Let us wind up.